Okay, assalamualaikum and a very good day to everyone. Thank you for watching my video. So in this video we continue on the previous video about the synchronization. And last video we learned about the critical section. Okay. So for today's in this video we learn about the hardware to support the synchronization. Okay, many systems provide the hardware to support for implementing the critical section code, as we looked at the previous video. And all solution below is based on idea of locking. So locking is one of the ideas in order to support the synchronization. Okay, using the locking, we try to protecting the critical regions or critical area through the lock. For uniprocessor, means a single processor, it have the ability to disable the interrupt. So currently running a code would execute without preemption and generally to inefficient the multiprocessor system. Okay, operating system using these not broadly scalable. So we have one mechanism locking, and then for a single processor it has to disable the interrupt. How about a modern machine, means the current machine, the new one? So the modern machine provides special atomic hardware instruction. So we have the atomic. So this atomic is for non-interruptible. So either test the memory words and set value, or swap the content or two memory words. So there is a mechanism that provided for the new machine, which called as the atomic. So atomic is the hardware for the modern machine. Okay. Here we have two functions that we call as the acquire function and release function. So in the coding part, it look like this one. Okay, they will do acquire lock because we use the lock as a solution. So acquire lock at the critical section, and release lock means that, let's say we have two process 1 and process 2. Process 1 is running, so we acquire this function lock for the critical section. So the other function, process 2, unable to slot into this critical section until when we call the function release the lock. So then the remaining section can be used by another process. So this is how we use the lock in order to solve the issue. Okay, the next part is about MUTEX locks. Okay. So the previous solution complicated and generally inaccessible to application programmers. So we have another part, MUTEX locks. So OS designer build a software tool to solve the critical section problem, okay, known as the MUTEX locks, the simplest part. So protect the critical section by using the first acquire, allow, then release function, okay, like the previous slide. And it uses the boolean variable for indicating if the lock is available or not. Okay, boolean variable to indicate either true or not true, true or false. Okay, so it will call the acquire function, and release function must be the atomic based on the modern machine, and usually implemented via the hardware atomic instruction. So atomic is the hardware that control this function. So however, using this kind of solution is require a busy waiting. So this lock therefore called a spin lock. So it's look like this one. We have the acquire function and we have the release function. So while not available, we have the busy wait here. Available is equal to false, and the release function part, available is equal to true. So this one is controlled by the boolean variable. Okay, and then here do acquire log, critical section, release log, remainder section while true. So this part is still similar. We still need acquire log, release log, but the difference, we have the busy wait here. Okay, we have the busy waiting. Another part is we call as SEMAPHORE. Okay. So usually when we talk about this part, we can you should know how to differentiate between the log and the SEMAPHORE. Okay, basically the MUTEX log is an object. Okay, the SEMAPHORE is variable, is an integer variable. So the MUTEX object allow multiple process to access a single shared resources at one time. Using the SEMAPHORE, so SEMAPHORE allow multiple process to access the finite instant of the resource until available part. So that is quite the difference between the MUTEX and SEMAPHORE, but both are used to handle or solve the issues of synchronization. Okay, we look at the SEMAPHORE. So synchronization tools that provide more sophisticated way than the MUTEX logs, okay, for process to synchronize their activities. So all the activities that we talk is in a thread. Okay. SEMAPHORE as integers variable, as I mentioned, that SEMAPHORE is the variable, MUTEX is the object. So it can only be accessed via two indivisible, which refer to the atomic operation, and it use the function wait and signal. So we have function wait and function signal. So originally we call as P and V. Okay. Definition of the function wait operation is based on this code: wait as the SEMAPHORE integer, while the SEMAPHORE is less or equal to 0, and then this part is busy wait, and we try to decrease the size of the S, refer to the SEMAPHORE. Okay, for the signal operation, signal refer to the number of SEMAPHORE and increment of the integer or the variable of SEMAPHORE. So counting SEMAPHORE integer value can range over an unrestricted domain. And binary SEMAPHORE integer value can range only between 0 and 1, same as the MUTEX logs. Okay, so now we have the counting SEMAPHORE using the integer value, and we have the binary SEMAPHORE. So the way it work like the MUTEX logs. So by using this part, it can solve the various synchronization problem in the process sync part, and consider, let's say, consider P1 and P2 that require the SEMAPHORE 1 to happen before SEMAPHORE 2. So we can create a SEMAPHORE synchronization initialized to the 0 value. So process 1 S1 signal synchronization, and we have process 2 wait for the synchronization. We have the SEMAPHORE value for S2. So this one can be implemented accounting SEMAPHORE as a binary SEMAPHORE. So we have two part. We can use the integer part, and we also can use the binary value. So in the SEMAPHORE implementation, must guarantee that no two processes can execute the wait function and the signal function on the same SEMAPHORE at the same time. So we use this mechanism in order to guarantee that part. So it cannot execute at the same time. So thus the implementation becomes the critical section problem, where the wait and the signal function are placed in the critical section. So now we have the busy waiting in the critical section implementation, but implementation the code is short. So little busy waiting is critical section really occupy that part. And note that application may spend a lot of time in critical section, and therefore this is not a good solution, because the application may spend a lot of time in the critical sections. So once if one process spend a lot of time at the critical section, that means another process need to wait for a longer time. So that is not a good solution. Okay, this part we have the SEMAPHORE implementation with no busy waiting time. So each SEMAPHORE that is associated with the waiting queue. So each entry in a waiting queue has two data item that we call as value and a pointer. Value is in integer variable type, and pointer to the next record in the list, means pointer will point to the next record in the queue or a list being that. So we have two operations. We have the block and wake up. So block mean we place the process, invoke the operation on the appropriate waiting queue, and wake up we remove one of the processes in the waiting queue and place it in the ready queue. So waiting we have ready, and after ready we can execute. So these are the codes: type, definition, structure, integer value, structure, process, list. So we have the list here, and then we have the SEMAPHORE. Okay, SEMAPHORE is the variable. So we have the wait for SEMAPHORE as, so as value minus minus, so we decrease the value of v value. So if the SEMAPHORE biggest the value or the value less than 0, so add this process to the list, and then call the block function. For this part, for the signal part, okay, if the SEMAPHORE bigger than the value and the value is less or equal to 0, so we remove the process P from the as list, from the SEMAPHORE list, and then we call the wake up function. So this one is the implementation of this that we call as two operation: main operation, block, and wake up. Okay, the next part we go for the deadlock and starvation. So if we don't have this deadlock and starvation are the problem and issues that can be occurs when we try to execute processes without the synchronization part. Okay, first we look at the deadlock. Deadlock means that two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes. Means that if one process need to waiting for the rest of the time, so that means it unable to be executed. So this is the process of deadlock. Okay, already lock the process to be executed. So in this part we have two SEMAPHORE to initialize part, process 0 and process 1. So we have the waiting time for the S, waiting time for the Q, and then wait for the Q, wait for the S, and then need to the signal before it can be executed. Okay, another part is about the starvation. Starvation means indefinite blocking. So a process may never be removed from the SEMAPHORE queue in which it is suspended. So this one another issues when we try to execute multiple processes. Yeah, and then we also have the priority inversion, means the scheduling problem when lower priority process hold a lock needed by the higher priority process. So that means we have the process that need to be executed, but it's being locked and hold by the lower priority. So we cannot proceed with another process, or we hang or stuck at that part. So these are the problem. So we want to avoid the deadlock from occurs, the starvation, and the priority inversion. Okay, another part is about the monitors. Okay, monitors a high level abstraction that provide a convenient and effective mechanism for the process synchronization. Okay, we have log, we have the meter log, we have the SEMAPHORE, and then we have the monitor. So this is abstract data type. Okay, internal variable only accessible by the code within the procedure, and only one process may be active within the monitor at a time. This one is not powerful enough to model some synchronization scheme, but it still can be used. So these are the illustration of how it's work. We have the monitor and monitor name, and set a variable declaration, procedure 1, procedure n. Okay, it can be procedure 1, 2, 3, 4, 5 until the procedure n, and we have the initialization code. So we use the monitors part in order to solve the issues of some synchronization. Okay, so this is the schematic view of a monitor. We have the queue. Okay, we have the shared data, and we have the operation here. So we have the initialization code here. So shared data, so it's based on the entry queue, refer to the queue. Okay, we use the condition variable, condition x and y. So two operations are allowed on a condition variable based on the variable. So x dot wait function means x call the wait function. So a process that invoke the operation is suspended until the x dot signal function being called. Okay, so we have the waiting part, and then x signal function. So resume one process, if any, that invoke the x dot wait. So this one to wait. Okay, this one is to wait. Okay, this one is to execute. So if no x dot wait function on the variable, then is no effect on the variable. So we use the condition of x and y here. So monitor with the condition variable. So it look like this one. Okay, generally it is similar like the previous one, but with the condition variable, we have the x and y condition inside the shared data. Before this, there is no x and y condition. So at the shared data, we just have the entry queue at the previous one, but in this monitor with the condition variable, we have the x and y. So x and y will call for the wait and for the signal. So after it get a signal, then it can resume the process. So a high level abstraction that provide a convenient and effective mechanism for the process synchronization refer to the monitor, and only one process may be active within the monitor at a time. So this one is similar like the previous one. So another mechanism is using the monitors. So monitors will based on the monitor's name, and it will monitor the process there. Okay, using the condition variable choices, if process P invoke the x dot signal and process Q is suspended in the x wait function, what would happen, or what should happen? So both Q and P cannot execute in the parallel, because one have the signal, another one has the wait. So if Q is a resume, then P must wait. That are the step. If we want to resume the Q, P need to wait. If we want to resume the P, so Q need to wait. So the option include signal and wait. P wait until Q leave the monitor, or it waits for another condition. Okay, signal and continue. Q waits until the P either leave the monitor or it wait for another condition. So that is based on the signal and wait part. So both has the pro and cons. Okay, language implementer can decide on that part, and monitor implemented in concurrent Pascal compromise refer to the language that we use. So P executing signal immediately leave the monitor, and Q is resume. So is still based on the signal and the waiting part. So implemented in other language including the Mesa, C# and Java. Okay, here is the monitor solution to dining philosophers. So monitor dining philosophers. Okay, example here, we have number thinking, hungry and eating, state 5, and then we have the condition set 5. So void pickup, we have the function integer 1. So state I equal to hungry, and test I. If state I not eating, it need to wait. Okay, so there are the condition inside the monitoring part. So another part, we have the put down. So here for state I equal to thinking, so I plus 5 and then divide by 5, this one to get the remainder. Okay, so it's continuous for this part. So basically it still use the signal and the awaiting and based on condition. So each philosopher I invoke the operation pickup and put down. You can refer to this code. We have the pickup and the put down, and we have the I. So dining philosophers dot pickup I, it will eat, and dining philosophers dot put down I. So no deadlock, but starvation might be possible in this case. So monitor implementation also can use the SEMAPHORE, means the variables. So SEMAPHORE MUTEX, initially we put the value as 1, and SEMAPHORE next, the value is 0. So integer next count equal to 0. Okay, we use the variable. So each procedure f will be replaced by, okay, example here we have the function wait for the MUTEX. Okay, and then body of the f procedures here, and then we have the condition if next count is bigger than 0, so signal for the next process, else signal the MUTEX. So mutual exclusion within the monitor is ensure. Okay, this part is using the variable. So the previous one using the SEMAPHORE, this one using the variable. So for each condition variable x, we have the SEMAPHORE x underscore sem underscore SEMAPHORE initially as 0, and then we have the integer x underscore count equal to 0. So the operation x dot wait can be implemented as here. Based on this one, x dot count refer to the counter here, a plus plus, and then if the next count bigger than 0, means next count bigger than 0, so we can give a signal, else signal is MUTEX. Okay, and then wait for certain time, and then x counted decrease. Okay, the operation x dot signal can be implemented as this one. Okay, if the x underscore count bigger than 0, so next count plus plus, and then signal proceed, and then wait for the next, and then next count will be decrease. So that is the logic behind the how we implement the monitoring part. Okay, this one is resuming processes within a monitor. So if several processes queued on the condition x and x dot signal function executed, which one should be resuming? Okay, if several processes queue, so we have several processes, let's say process 1, process 2, and process 3 in the queued condition, and then x signal is executed, means we call the function of x dot signal. So which one to be executed first? Okay, first come first serve frequently not adequate. So conditional wait and construct for the form x dot wait C. So C is referred to conditional wait. So where C is priority in the numbers, so process with the lowest numbers higher priority is scheduled the next. Based on this part, we don't use the FCFS, but we use the priority part. So it's based on the priority number of each processes. Okay, here we have several processes, so it depends on the C, which refer to the priority number of each processes. Then it will select which process that should be proceed or execute. Okay, so that's end of the part 1 for the synchronization. So hopefully you're able to know that there are several things that we need to avoid in the processing or resume the processing. We need to avoid the deadlock, we need to avoid the starvation, and we also need to avoid the priority inversion. And then there is mechanism that we can use for the synchronization. We can have the lock, we can have the muted lock, we can have the SEMAPHORE, we can use the monitor. So that's all for part 1. Thank you and Assalamualaikum.